Hi guys, welcome to your video, your first pre-cal video about functions and analyzing functions. So the first thing you want to recall from maybe Algebra 1 or Algebra 2 is the definition of a function. The definition of a function is, so there are many things that you can graph and make a table of and make a little map diagram of that aren't considered functions. So let's start with what would be considered functions. Alright, so here we have a set of data points that represent the input and a set that represents the output. This could be your input is usually your x values and the output is usually your y values. Okay? Each of these has only one of these. So let me draw you an example and then I'll draw you a non-example. So this would be an example of a function. So I know there's a couple arrows to keep track of, but each of these inputs has one arrow pointing to only one of the outputs. So one here, one here, one here, one here, one here. So every input has exactly one output. This relation can also represent a function. The new data points that I drawn are in green. So if you notice, this input has exactly one output, and this input also has exactly one output. They can share the same output. Each input can share the same output. As you can see here, this input, this input, and this input, this x, this x, this x, has the same y value. So that is good. This is an example of a function. Now let me show you an example of something that's not a function. So this would be a non-function, because we want to go step by step to see if each input has exactly one output. So this input has an output, exactly one output. This input has exactly one output. But this input, you see how it has two arrows going to two separate y values? That cannot happen. This input has two outputs, and the maximum is one. So if it has more than one output, it is not a function. So graphically, these two would represent functions because each x value has only one y value. So one way to test that on a graph is to use the vertical line test. What you do is you take a vertical line, in my case I'm going to use a ruler, and you scan the graph, you put it vertically on your graph, and you scan it from left to right. What you're doing is you're checking to see if the graph intersects this vertical line more than one time. So as you can see here, if I keep going, it's only going to hit one time. So this parent function is the quadratic function. It is a function, and it satisfies the definition. Each input has exactly one output. Same thing over here. If I do the same thing, if I scan, it's only hitting once there, 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 throughout the entire graph, so that would represent a function. This one, by the way, we'll learn our parent functions later on in the week, is called an exponential function. So now I'm going to show you some examples of non-functions. These are non-functions because I'm going to do the same thing with my vertical line. I'm going to apply the vertical line test, and we're going to see that at multiple points, there are two y values for one x value. So if I look here, if I'm scanning from left to right, if I stop right there, I can stop at multiple places. But you see I have a y value here and a y value here, one on the bottom, one on the top, for the same x value. And as long as it happens once, it is not a function. So it happens there, I'm done. That is not a function. Over here, I can see if I'm starting to scan the graph from left to right, as I start out, it looks good, it looks promising. It looks like a function. But then, once I get to a certain point, let's say right here in between, now I can notice that it has 1, 2, 3 y values for this one x value. So it is not a function because it does not pass the vertical line test, but more specifically because it has multiple y values for one x value. Okay? So right there I can tell it's not a function, even though if I keep going further, eventually it looks like it turns back into a function. But that's not how it works. It's either a function or not function. It's not a function for part of it and a non-function for the rest of it. It's one or the other. Alright, so that other stuff was pretty basic, just using the definition. Now we're going to actually analyze functions, which is what you need to be thinking every time you come across a function. So to analyze a function or a graph or an equation, one important, the most important if you ask me, characteristic is the zeros. So while you're taking your focus notes, a question you could ask yourself is, what's another word for zeros? I will not answer that. I'll let you guys look that up in your notes. But to find the zeros of the function, you're going to do one thing, well, two things really. Set f of x equal to 0. Now, once you do that, all you're going to do is, I'll put a step here, solve your equation, or solve for x. Okay? So you've set your equation equal to 0, much like we did with the quadratic formula, and then you're going to solve for x. So sometimes that requires factoring, sometimes it's just algebraic manipulations of a function. So let me show you how to find the zeros of a function. Alright, so to find the zeros, you don't necessarily need to know what the function looks like, although we will be identifying what functions look like based off their parents. But if I look at this equation, f of x equals square root of 2x plus 5, I'm finding the zeros of that. So all I'm going to do is set the function equal to 0 and solve for x. It's pretty basic, so it becomes an equation that we can solve for once we've set it equal to 0. So this is a square root function. We'll learn what that looks like later on if you don't know already. But it is one of our parent functions, and we can use that to graph the function later. But again, what I want you to start thinking of first is always the zeros. So I'm going to set this whole thing, equation, equal to 0. So 2x squared 2x plus 5 is equal to 0. If you'd like, you can go ahead and write the 0 on the other side. I like doing that, so that I have what I'm solving for on the left and my 0 on the right. Well, exponent, this is an exponent. The square root is an exponent. So how do I get rid of it? I square both sides. So I would square this entire thing, and I would square the left side. When I square the right side. When I square the right side, 0 squared is just going to give me 0. When I square the left side, what happens? Well, my square and my square root cancel each other out, and they leave me with 2x plus 5. This becomes a super duper, well, let me write that 2 again, a little bit prettier. This becomes a super duper easy problem to solve. All I got to do is get rid of the 5, then get rid of the 2. So subtract 5, 2x equals -5, divide by 2, and I get x equals -5. So my 0 of this function is -5 over 2. All right, now I want to find the zeros of g of t equals t squared plus 5t plus 4. So this is the same thing as the previous example, except now I'm using g of t. I'm using different variables, right? But I'm going to do the same thing. So my steps are for f of x. So instead of setting f of x equal to 0, I'm going to set g of t equal to 0. So I'm going to do the same thing. I'm going to say 0 equals t squared plus 5t plus 4. And remember, I like having the 0 on the right side, so I'm going to go ahead and put this over here. Now, you could be thinking to yourself, there are several ways to solve this when you have a quadratic. We've already looked at those ways. One of them is by factoring. The other one is by using the quadratic formula. I want you guys to think, if you can factor, because it's way easier than plugging in all these numbers. So since I can factor this, or I'm going to try to factor this, I'm going to go ahead and split that up as t squared goes here and here. So I'm not going to be writing those arrows anymore now that we've already had our practice. And then I want to split up 4. I can write my side work over here, my scratch work. Find the factors of 4 that adds to give me 5. 1 and 4, 2 and 2. Well, which one's going to work? The 1 and the 4. So I would write them here, plus 1 plus 4. Remember, since it doesn't have a coefficient of, since it has a coefficient of 1, then I don't have to worry about the a times c. I just have to worry about the c. So plus 1 can go there, or plus 1 can go there. Either way, doesn't matter. Equals 0. Okay, so this is something I did not talk about, but the whole reason we learned factoring is because once we have factored, if you think about this real quick, well, if this times this gives you 0, let's isolate it real quick. What would this have to be? If this times this gives you 0, one or the other would have to be 0, right? That's the only way you can get two numbers to multiply and give you 0. Either the first number is 0 or the second number is 0. So we're going to take this as both numbers. What happens when both numbers are 0? And those are both going to be my x-intercepts, or my zeros here. So if I take this equation, well, this factor, and equal it to 0 by making it an equation, and I solve for t, I'm going to get -1. That is one of my zeros, or my x-intercepts, whatever you want to call them, or t-intercepts in this case. The other one comes from setting this one equal to 0. So again, if t is equal to -1, I plug in -1, I get 0 times some other number. It's still going to be 0. It doesn't matter what this other number is. Then, if I do the same thing with t plus 4 and equal it to 0, notice how I make my t's like a little curly at the bottom so I don't confuse them with pluses. So just FYI. If I subtract 4 from both sides, I get t equals -4. In other words, if t is -4, I plug in -4 here, I get -4 plus 4 gives me 0, times this, who cares what it is, it's still going to give me 0. So that's why we set both of the factors equal to 0 to solve for zeros or x-intercepts, whatever you want to call it. So again, the big thing to take away from these two examples is that you set the function equal to 0, and then you use algebraic processes to solve for the variable. Okay? So in this case, we set t squared plus 5t plus 4 equal to 0. The algebraic process that we use to solve that is factoring. Once we factor, we set each factor to 0, and then we got our answer. The previous one, involved the square root, where we just set the function equal to 0, and then we just got rid of everything outside the parentheses, slowly but surely, outside of t. And then we ended up with the number. So the general idea is set the function equal to 0. That's all you need to know. I think this part will follow once your brain will finally kind of catch on once you figure out you're setting the function equal to 0. All right, so just so you can see this on a graph, we've done this algebraically, but on a graph, a 0 is where the function equals 0. Now, where is that? Well, what's another word for 0? X-intercept. And it makes sense because that's where my y value is 0. That's why we're setting the function equal to 0. So even if I don't know what this function is, which you don't yet, all you got to do to find the zeros is see where they cross the x-axis. So right here, that would be one of my zeros. So if I count, this is 0, -1, -2, -3, -4. So one of my zeros is the coordinate point -4, 0. Okay, so we can write that as a coordinate point as well. Over here, my next one is right over here. It looks like it's at -2, 0. So on and so forth. My next one is here. It looks like that's passing at the origin, so 0, 0. And then finally 1, 2, 3. It looks like that is my final x-intercept, 3, 0. So again, if I really look at this, to kind of take it home with the fact that what are all my y values equal to? They're all equal to 0. And another way to say y is f of x. That's why we set the function equal to 0. All right, so finally we're going to talk about y-intercepts. Y-intercepts are where they cross the y-axis. That's where the x value is equal to 0. So your only step here is to plug in 0 for x, and then it follows to simplify. So let me show you an example. Okay, so what we're going to do here is we're going to set my x values in my function equal to 0. So really what we're doing, if I take all these x's and replace them with zeros, I'm left with this. F of 0 equals 0 plus 9 minus 0 minus 3. So this is another way to write the y-intercept. So instead of writing the word y-intercept, you can write f of 0 or g of 0 or whatever your function looks like. So all you got to do now, you're not going to leave it like this, obviously, you're going to simplify. So 0 plus 9 gives me 9. 0 minus 3 gives me -3. If I divide 9 by -3, I get -3. So my y-intercept is equal to -3. This is another important characteristic to being able to graph a function or analyze a function. All right, so the last characteristic that we'll talk about today when you're analyzing functions is you want to determine whether the function is symmetrical with respect to two things. So one category falls into odd, we'll talk about that, and even. So if the function is odd, then the function reflects with respect to the origin. So I've written it here for you. It reflects with respect to the origin. So what this means, basically, is that if it's in the top right, if there's a part of the graph in the top right, the first quadrant, it reflects over the y-axis and then over again on the x-axis. So graphically, an odd function looks like this, where it looks like if I reflect this across the y-axis, it would kind of look something like this. Right? If I reflect this right side across the y-axis, it looks something like this. And then if I reflect it one more time across the x-axis, now it looks something like this. So the symmetry should look something like that on both sides, where it's flipping across the y and again across the x. So here's another example. Now I can look at the left side and make me understand the right side. So if I look at the left side and I reflect it across the x, it's going to look something like this. If I just look just on the left side, the y-axis will reflect across like this, looking like a W. If I don't see the right side, just the left side. Now if I take this, the right side of this W, and reflect it across the x again, now I have the right side of this graph, which makes it an odd function. Oops. All right, let me get you two more examples of odd functions graphs before we move on. So this function would be odd as well because it's, again, holding the same characteristics of a reflection across the origin, across the y, and then across the x. So if I reflect this across the y-axis and I trace it in the green, I get something like this, ish. Then if I take this green and then reflect it across the x-axis, now I have my original function, the other side of that original function. So that is one way to show that it is a odd function. All right, so let me show you one last example. Now it doesn't matter whether you go y first, then x, or x and y. I'm going to give you the same thing. So let me show you what happens if you reflect it across the x first. If I were to reflect just this left-hand side of the graph across the x-axis, I would be reflecting this down over here, so it would look something like that. And then I would reflect this part up, so it would look something like that. So that would be if I reflected across the x-axis first. If I now reflect this across the y-axis, now this part is going to look something like this. That's what this part, this little hump would look like. And then this one would be on the bottom over here. So you could see how that is also an odd function if I erase that first reflection. So as long as you get the same thing on the left and the right after doing both those reflections, then it is an odd function. So we've already seen what the odd function symmetry looks like. Let's look at the even. The even is a reflection with respect to the y-axis only. So it's only doing one reflection. It looks the same thing on both sides. Looks like the same thing on both sides of the y-axis. So this one's a whole lot easier to explain. Let me give you one example. So I have this W-looking thing here. You can probably already see if I look at the left side and compare it to the right side of the y-axis, then you can see that it looks like the same thing. But if I take this guy, and again, reflect it with my tracing method across the y-axis as best I can, it's going to give me the same graph that's already there. So that's how I know it is an even function. So here's another example of an even function, the most basic one, which is our quadratic or our parabola. If I just go the opposite direction, if I try to make the right side reflect across the y-axis, then I would be tracing this side just as so, and it's going to give me the same graph that I already have on the left, making this an even function because it's symmetric with respect to the y-axis. And finally, let me show you this even function over here. I'll erase this odd one over here. If I look at both sides of the y-axis, I'm going to see that it's the same general thing. I might not have spaced it out correctly. But if I take this side and then reflect it over here, I'm going to get this green dotted part, which is already there from the y-axis, or from the function. It's already a symmetry with the y-axis. So again, odd's a little bit tougher to do. Even is a lot easier to see. It's just one reflection, where odd is two reflections across the y and across the x. So a big reason why symmetry is important is because it makes functions easier to graph. If you know a function is already going to be even, and you already know one side of the graph, you just reflect the other side across the y-axis, and then you got your whole graph. Same thing with odd. If you know that a function is odd, and you already have the left side of your graph, you just got to do a double reflection across the x and the y, and then you have the other side of your graph. So algebraically, odd functions follow this equation. If I plug in negative x and get a negative f of x, then my function is odd. If I plug in the same value, negative x, into an even function, and I get a positive f of x, then my function is even, and it will be symmetrical with respect to the y-axis. So let's see what that looks like in the odds case. If I plug in a negative x into every single x here, and it looks like the same thing as my original function, just with the signs flipped, that's what this negative means, then I know I have an odd function. So let's go ahead and do that. Let's go ahead and plug in a negative x everywhere we see an x. So this will be 3 times parentheses, I'm going to plug in negative x in a minute, plus parentheses, I'm going to plug in that negative x. Now, so I'm plugging in negative x for every x that I see. So if I simplify this, then I get negative x cubed is negative x times negative x, which is x squared, times another negative x, which is negative x cubed. If I multiply that with positive 3, I get a negative 3x cubed. And then plus a negative x would give me a negative x. So this is what I get after plugging in negative x. Now, is this the same thing as negative f of x? Well, let's see. negative f of x is the same thing as negative of this whole thing. Negative of my function. My function was 3x cubed plus x. So basically this last step is asking me, is this the same as this? Well, all I would have to do is distribute this negative here and here, and then I would see that I'm going to get the same thing. Negative 3x cubed plus negative x gives me the same thing as f of negative x. So negative f of x equals f of negative x. So that tells me that it is an odd function. You can check there. So again, the property for odd was if I plug in a negative x, then I get a negative f of x. For even, it stays the same no matter what I do to it. So if I plug in negative x, it should stay the same. So what I'm going to check for is when I plug in negative x to this function, nothing changes. So let's go ahead and try that. Let's make sure that that happens. We're testing for an even function. So I'm going to plug in negative x for x. So this should give me f of negative x equals, I'll put parentheses, I'll fill it in later, but I'm going to put parentheses to the power of 8 minus, and then there's no x to plug in here, so minus 15 stays like that. And again, I'm plugging in a negative x for f of x, or for x, I'm sorry. So all I got to do now is simplify. F of negative x becomes, what happens if I take negative to the power of 8? I can keep multiplying negative x times itself 8 times, or I can realize it's an even power, so it's going to come out positive, because a negative times a negative is a positive. So this should be a positive x to the 8th, and then nothing is happening with this minus 15, it is staying the same. So the question is f of negative x equal to what I was given? Well, let's write f of x right under it. F of x is x to the 8th minus 15. Are those two the same? Yes, they are, so it must be even is my function. I could put check marks by those just to verify that though that function, x to the power of 8 minus 15, would be an even function. Alright, so to sum it all up, when we're analyzing functions right now, the key points or the key characteristics are the zeros, which you get by setting the function equal to 0 and solving, the y-intercepts, which you get by plugging in 0 for the x's and simplifying, and then the symmetry. You got to figure out if it's odd or even, and remember, if it's not either of those, it's going to be neither. There will be no symmetry that you can use to do a shortcut. So those three things we're going to pick up more throughout the class, but starting with those three things, you need to know those basic